A function is a collection of ordered pairs, x, y, such that for every x there's exactly one y. So let's look at some examples. These are really basic examples. So it's simply a collection of ordered pairs. So in this particular set that I'm writing here now, we only have 3 ordered pairs. That's not a typical function, but for purposes of discussing what a function is, it's that simple. It's any collection of ordered pairs. In this case, we have 3. So because we can list them like this, we just list the ordered pairs, and we use these brackets here to indicate that it's a collection or a set in mathematics. And this is a function because, first of all, it's a collection of ordered pairs, but secondly, every x value is mapped or sent to a one y value. So the input, if the input is 1, your output is 2. So x is 1, y is 2. Here, if your input is 3, your output is -1. So x is 3, y is -1. Here, we have x is -5, that's your input, and y is 2, that's your output. So there's exactly one y for every x, so it is a function. This collection of ordered pairs is not a function. And that's because you'll notice here that if our input is 1, our output is either 2 or 5. You can't have 2 different outputs for one input. And the purpose of that is, the reason why we want functions to behave that way is because it resolves, or it takes care of ambiguity. With a function, you know exactly what your output is going to be for a given input, okay? You don't want the ambiguity of wondering, well, what if I put in a 1, is it going to be a 2 or is it going to be a 5? You don't want that, because that does not function very well in the real world, okay? So we eliminate that possibility for functions. So this one is a function and this one is not. Now let's look at another example from the real world that you all are familiar with, and that would be the area of a square. The area of a square depends on the length of the side for the square. Okay. So there's our square, and the 4 sides are all the same length. Let's call that x. And so the area is a function which depends on x. So x is the independent variable, and the output, the a of x, is the dependent variable. The area depends on x. And the way we calculate the area is we square the length of the side, or x. And this is function notation. We can think of this as y equals x squared. So x is the independent variable. Is that kind of blurry? Let me see. Y is the dependent variable. Okay. And if I graph this, normally, if I wasn't talking about area, I would just graph the entire parabola. But because we're talking about a square having a x as the length of its side, we can't have x being negative, right? Squares don't have negative sides for their length, and they can't be 0 either, because if it's 0, then it's not a square anymore. So we have to exclude 0 and all negative numbers. Now, I'm talking about x, right? X is where we have to exclude the negative numbers and 0. So I'm going to use a circle to show that I'm not including 0. And I'm going to plot these points. So if I square 1, I'm going to get 1, right? So that's 1 point. If I square 2, I'm going to get 4. So that's another point. And so we're going to have a parabola like this. So we have two representations for our function. We have y equals x squared. This just describes the relationship between the input and the output. In this example, we listed the ordered pairs, but we can't do that here because we have infinitely many ordered pairs. So in this example, instead of listing the ordered pairs, we can simply write the equation, or we can graph them. So every point on this curve here represents an ordered pair for our function. So, and every ordered pair xy can be represented by an equation, y equals x squared, okay? So those are two other ways of representing functions besides just having a list of the ordered pairs. Now, because our area or the length of our side is positive, we have to restrict the domain. This is a polynomial, and normally the domain, just standing alone, would be all real numbers. But because we're talking about a square with length x for its side, the domain, which is all possible input, is the set of all x. And this is the way I write that. Set notation uses this bracket here, the set of all x, such that, that vertical line there is replacing the word such that, x greater than 0. And this is called set builder notation. So how do we know that this is a function? Well, when you have a graph like this, you would use the vertical line test. And it answers, the vertical line test answers the question, is your graph a function? So in order for a graph to be a function, each vertical line must only intersect once. And if any vertical line intersects more than once, the graph is not a function. Let me write that out for you. All right. Again, in order for a graph to be a function, each vertical line must only intersect once. And if any vertical line intersects more than once, the graph is not a function. So all it takes is one line for it to fail. If you can find one line where it intersects twice, then you know it's not a function. But this is a function, okay? Every single vertical line that I draw intersects exactly once. So basically what's happening here is if I draw a vertical line here, what you're really doing when you draw a vertical line in the rectangular coordinate system, you're picking an X, because that vertical line is going to cross the X axis. And so right there, I'm picking an X. But that X value corresponds to a point here. And so if you want to find the Y value that goes with that X, you would extend it over to the graph. And then that would be your Y2, or Y1, sorry, X1, Y1. Okay, so for every X, there's exactly one Y. Let's look at an example of a relationship between X and Y where it's not a function. It fails the vertical line test, so you can see how that works. Any questions on this before I move on? Okay. Feel free to unmute yourself if you're zooming in, if you want to interrupt, and if you have a question, you're certainly welcome to do that. I like to interact with students because sometimes, since I know the material so well, I might talk over your heads and I think, oh, this is obvious, but it may not be obvious to you simply because you don't have the experience that I have. So just interrupt me if you feel like I'm talking over your head or something. Chances are somebody else has the same question. All right. All right, so here I'm going to draw a circle. Let's just say it has radius 1. Centered at the origin, okay? And that obviously fails the vertical line test. Right away you can see that if any vertical line I draw, except for one on each end, is going to pass through twice. And that's because if I pick an x1, I don't just have a y value from this point, I have another one down here. So I have two y values for one x value. That's not a function. You can only have one y value for every x. So notice I use the word relation. A relation in mathematics is simply a collection of ordered pairs. A function is a relation with the added stipulation that there's exactly one y value for every x value. So every function is a relation, in other words, a collection of ordered pairs, but not every relation, and this is an example, is a function. Functions are a subset of relations. Okay, so this is just a collection of ordered pairs. All right, so let's talk now about function notation. Oh, before I do that, I forgot. Let me just show you a little bit more about this circle here. If you look at the equation, x squared plus y squared equals 1. This is the equation for this graph, okay? And if I solve for y, you'll notice that I subtract x squared from both sides. So and that gives me that y squared is 1 minus x squared. And then to isolate the y, I take the square root of both sides. But when you take the square root like that, what you get is that y could be plus or minus the square root of 1 minus x squared. That's where your two y values come in. You've got a positive and a negative. So here, this is the positive and this is the negative counterpart. And so here's the graph using the vertical line test. Here's the equation. If you didn't have the graph and you just wanted to show that it was not a function by, you solve for y. That's the trick, solve for y. Because when you have it in this form, then you can replace y with your function notation. So that's what we're going to talk about right now, function notation. Function notation simply replaces y with f of x. In other words, y equals f of x. So that tells you that the function values are y values. Whenever someone says to evaluate a function, you're looking for a function value. That means you're looking for a y value. Oops. So really, to evaluate a function given a certain x just means you're looking for the y value that's paired with that x. So if you have a graph, you would draw a vertical line. So let me just look at an example. Okay. Here's a graph. This is a linear function. Notice it passes the vertical line test. Every vertical line will only intersect that line one time. Okay, so it passes the vertical line test, therefore it is a function. If I write the equation of this linear function, it's y equals 3x plus 1. The slope is 3, the y-intercept is 1. And if I want to write it in function notation, I just replace the y with f of x. So f is the name of the function. Typically we use a letter. So for example, for area, I used a of x because a represents the area. Here I'm just talking about a general function, so I use f. F is most commonly used to name a function in a problem. So I picked f. This parenthesis here just shows you that your input is x. So if I want to evaluate f at 3, I plug in 3. So f of 3 equals 3 times 3 plus 1. Okay? F of 1 equals 3 times 1 plus 1, which is 4. That's 10. So f of 3 is 10, f of 1 is 4. Now, this is if you're given an equation, and this is how you evaluate. So I'm given 3, I'm finding the y value that goes with that x value. So the point 310 is a point on the graph. Similarly, 1, 4 is a point on the graph right there. So if I want to evaluate from a graph, you take your x value and you draw a vertical line, and I didn't draw mine very straight, but we'll just pretend that's a vertical line. So if I put in 1, I go to the graph until I get that point, and the output is on the y-axis, so 1, 2, 3, 4 is the output. So I don't even need the equation if I have the graph. You can evaluate it from the graph, or you can evaluate it from the equation. Okay? Any questions on that? We're going to do this a lot, and in my experience, even students who have gone through college algebra and are taking calculus, sometimes it gets confusing. Which are the x values and which are the y values? And just remember, your x values are always your input, and your y values are your output. Okay? I have one more thing that I want to cover before we finish today, and that is what interval notation is. Oops, that's not true. I forgot. I have another page here that I have to cover before we get to that. Whew, I thought I was almost done here with this mask. I get kind of faint at the end of the day. This is my fourth class. No, my third class. I still have one more. Whew, it's kind of wearisome, but we're going to make it through this. All right. Domain of a function. As the example with the area, we had to restrict the domain because you don't want to have negative values for the length of your side. So the domain of a function is a very important concept, and it simply means all possible input values. And remember, input values are x values. The range of a function is all possible output values. And these, of course, are y values, or we call them function values. A lot of terminology here to learn, but you'll get the hang of it. Okay, so for example, I don't like that color, I'm gonna switch. P of x equals 7x to the 5th minus 2x cubed plus 3x squared minus x plus 100. Okay? This is a polynomial. It's a collection of powers on x, which are added or subtracted and multiplied by coefficients. So anything in that form is a polynomial, and the domain is always all real numbers. Okay? Standing alone. Obviously, when we did the area example, that was in a certain context. So y equals x squared is a polynomial. So normally the domain would be all real numbers, just standing alone. But because we were talking about a square, we had to restrict the domain. So in a lot of these examples, when we're getting into business applications, most of the hopefully most of the problems will be business related. You all are business majors, right? Or in the business department. Most people taking this class are. So within a context like that, the domain is always going to be restricted according to what the situation is for the example. So if I have a function like f of x equals 10, this, by the way, is a constant function. And this also has domain being all real numbers. And the way we could, another way of writing that is d equals, we can write it like that. That's, sorry, r is a, with the two lines like that is another way of writing real number system. And if I want to graph this, here's a height of 10, and so the graph is the horizontal line that passes through that 10 there at on the y-axis. That's a constant. Notice the height of that function is always the same. So you can think of function values or the output as the height of the graph. So because it's a constant function, in other words, it's always 10, it will always be at the same height. So that's why you have a flat horizontal line. And then, of course, we talked about this example earlier, 3x plus 1. That's also a polynomial. Remember, that's the line that we just looked at. Linear functions are polynomials, okay? So they also have domain, all real numbers. All right, now what if you have a function like this? Y equals 3 divided by x plus 1. This is not a polynomial. This is a rational function. There's a problem with the variable being in the denominator. So rational functions have the numerator is a polynomial. There's a constant 3, that's a polynomial. And the denominator is a polynomial that has degree greater than or equal to 1. In this case, x plus 1 has degree, it's a degree 1 polynomial. That's the power on x is 1. And because it's in the denominator like that, we could conceivably have 0 in the denominator. We're not allowed to divide by 0. So we have to restrict the domain here for this function. It's not all real numbers. We have to exclude what number? Anybody? -1. We have to exclude -1 because if I substitute -1 in for x, I'm going to be dividing by 0. Can't do that. So now my domain is going to be expressed in this way. In set builder notation, it's the set of all x such that x is not equal to -1. So like I said, this is set builder notation, and we can graph this. So here's my number line. Here's -1. I don't want to include it. So in order to not include a number, we use this open bracket or parentheses, if you will. So that shows that our function is everywhere except at the point -1. I mean, that's our domain, is what I meant to say. So it's the entire number line, and over here we have -infinity, here we have -1, and here we have positive infinity. So if we want to write this in interval notation, the graph helps. It helps you because you read from left to right, and you start with -infinity. You get up to -1, something happens there, and then you pick up at -1 and go off to infinity. And because -1 is not included, we use an open bracket for that. And you can see there's my open bracket. And -infinity and positive infinity, we don't want to include those either because you can never reach infinity. So we use open brackets for those as well. and we join the two intervals together. So this interval represents this half, which is less than -1, and this interval represents the positive side of -1. So we have two intervals joined together, and this is our domain. So this is set builder notation. That's what we call it. And this is interval notation. All right. You need to be able to go back and forth between the two. So let's look at some more examples.